Biomechanics is the study of living organisms and factors that act on the body. Throughout this task, I will be investigating the biomechanical principles that affect the velocity and flight of a basketball throw throw. By applying biomechanical concepts such as Newton's law, equilibrium, force summation, through kinetic chain and lever systems, I will evaluate how these factors contribute to performance. This analysis will focus on Steph Curry's three-throw techniques and compare it to my own performance. Steph has been selected due to his exceptional accuracy and consistency, as he is widely recognised for being one of the most successful free-throw shooters in the world. A basketball free-throw consists of three fundamental phases: preparation, execution, and follow-through. Each phase plays an important role in ensuring effective force production, control, and accuracy is being applied. In the preparation phase, Steph establishes equilibrium, which is important for balance and stability. This occurs when all forces acting on the body are balanced, meaning there is no acceleration. Initially, Steph is in a static equilibrium, where his body is stable and controlled before movement begins. As he bends his knees and prepares to shoot, he transitions into a dynamic equilibrium, where his body is moving out but remains stable as the forces acting on it are balanced. A key factor influencing equilibrium is the centre of gravity, which is the point where the body's mass is evenly distributed. Steph lowers his centre of gravity by flexing his ankles, knees, and hips, which increases stability. His feet are positioned approximately shoulder width apart, creating a stable base of support, with one foot slightly in front of the other and both feet are pointing directly at the ring. This stance improves balance, allowing him to have more control. This stability is important as it allows force to be applied effectively in the correct direction. If his balance was unstable, force would be lost, reducing both accuracy and consistency. Before initiating the shot, Steph holds the basketball in his hands, demonstrating Newton's first law of motion, as the ball remains at rest until acted upon by an external force. This is the beginning of force summation, where his force is generated by different body parts and combined in a specific sequence to maximise total force. During the execution phase, Steph generates force through summation of momentum, using a kinetic chain. This process begins in the lower body, where his ankles, knees, and hips flex and then extend after bending. As these joints extend, Steph applies a downward force into the ground through his feet. According to Newton's third law, action produces an equal and opposite upward force from the ground, known as the ground reaction force. This force is what drives his body upward and initiates the transfer of momentum through the kinetic chain. Because Steph maintains equilibrium during this phase, the force is transferred up the kinetic chain rather than being lost. The movement follows a paroxysmal to discal sequence, meaning the force is transferred from larger body segments to smaller ones. As Steph transitions into the shooting motion, momentum is transferred from his legs through his core into his shoulders, arms, and finally into his hands and fingers. This allows him to generate sufficient velocity onto the basketball without relying just on his upper body. This efficient transfer of momentum allows Steph to apply the optimum amount of force needed to achieve the correct velocity and trajectory. In a free throw, the aim is not to maximise force, but to apply a controlled and precise amount of force. An effective kinetic chain enables for smooth, consistent force generation from his lower body, reducing reliance on his upper body and improving accuracy and consistency. If this sequence was done wrong, it would result in a pushing motion, reducing both control and shooting accuracy. The human skeletal system has a lot of levers, with the majority being third-class levers. These levers have the effort applied between the fulcrum and the load, meaning they prioritise speed over force. As Steph takes his three-throw, his body acts as the lever, the elbow acts as the fulcrum, the basketball is the load, and the primary effort for extending the arm is applied by the contraction of the tricep and forearm. This allows the arm to extend rapidly, which provides the force to accelerate the arm and the ball. Additionally, the wrist acts as another third-class lever, providing the final flick at the end of the movement. This wrist action is crucial as it controls the ball's trajectory, backspin, and improves accuracy. This is achieved through precise flick of the fingers, which generates backspin to stabilize the flat path of the ball and provides a softer rim impact. During the follow-through phase, Steph maintains the movement after releasing the ball, avoiding unnecessary deceleration. This helps transfer the full momentum to the ball, maximizing efficiency. In comparison to Steph's free throw, I've analysed my own technique to identify biomechanical differences affecting my performance. In the preparation phase, my equilibrium is significantly reduced due to my stance. Although my feet are shoulder width apart, my left foot is positioned behind and raised onto my toes, while my right foot remains flat. This decreases my base of support and shifts my line of gravity towards the edge of the base, reducing stability. This lack of balance negatively impacts force generation, as an unstable base limits the efficient vertical transfer of force through a kinetic chain. As a result, the force is not directed vertically through the body and is lost through unnecessary adjustments, causing inconsistencies in force direction, leading to a deviation in the ball's trajectory and reduces shooting accuracy. Additionally, I am able to maintain consistent balance and tend to lean too far forward during setup. This shifts my centre of gravity outside its optimal position, requiring adjustment during the shot. This negatively impacts the performance by reducing control and causes inconsistencies in the direction of the force applied to the ball. In contrast, Steph maintains a stable and balanced base in his three throws, allowing for greater repeatability. During the execution phase, a key limitation in my technique is the insufficient force summation. My knee action is inconsistent as I tend to bend, straighten, and then bend again during my routine. This disrupts the smooth transfer of force from the lower body to the upper body. This reduces the effectiveness of impulse, as force is not applied consistently over time, decreasing the impulse generated. This results in insufficient and inconsistent momentum being transferred to the ball. Due to this inconsistency, I compensate using my upper body to generate additional force. This places a greater demand on my smaller upper body muscles, which are less capable of producing consistent force and power, compared to the larger muscles in the legs, resulting in a greater variability in the shot distance and reduced control over ball trajectory. This limits the application of Newton's third law, as less force into the ground results in a weaker, equal, and opposite reaction force. As a result, less momentum is transferred through the lower body through the kinetic chain, reducing the overall force applied to the basketball and reducing the velocity the ball is released. In contrast, Steph efficiently transfers force from his lower body, allowing for a greater momentum and control in the shot. Due to this insufficiency, my shot becomes more of a push rather than a smooth, coordinated action. This further disrupts force summation as force is not transferred sequentially from the lower body through to the upper. In terms of levers, my shooting arm functions as a third-class lever. However, its effectiveness is reduced due to poor arm alignment during the shot. As my arm is not aligned towards the target, the force produced is not applied in a straight line, resulting in reduced control over the direction of the ball. At the point of release, inconsistencies in my wrist action further limits performance. I flick both wrists and fail to consistently direct my fingers towards the ring, causing lateral force to be applied to the ball, which disrupts the ball's flight path and reduces accuracy. In contrast, Steph demonstrates a controlled flick of the wrist, producing consistent backspin and improved shot stability. This inconsistency in force application reflects Newton's second law, as variations in force leads to change in the ball's acceleration. This results in inconsistencies in both shot distance and arc, ultimately affecting the overall trajectory. The most significant limitation in my performance is the insufficient force summation through the kinetic chain, as this has the greatest impact on release consistency, the ball velocity, and overall shooting accuracy. To further evaluate my performance, I analysed the projectile motion on my 3-throw and compared it to Steph's. This analysis focuses on key factors such as the angle of release, height of release, speed of release, and how these influence the accuracy and consistency of the shot. The angle of release is a key factor in determining the projectile's flight path. In my performance, the release angle is approximately 65 degrees, resulting in a flattened trajectory. This reduces the vertical component of the motion, lowering the entry angle of the ball and limiting the margin for error, making the shot less forgiving. In comparison, Steph releases the ball at approximately 69 degrees, creating a higher arc and a steeper entry angle. This increases the margin for error, allowing the shot to remain successful, even with slight inaccuracies in force or direction. The height of release also plays a significant role in the projectile motion. In my performance, the release height is lower due to the limited extension through my ankles, hips, knees, and shooting arm during the execution phase, as well as my short stature at 5'2" compared to Steph at 6'3". This reduced vertical release results in the ball being released from a lower vertical position, producing a flatter parabolic trajectory. A lower height of release also decreases the entry angle, further reducing scoring accuracy. To compensate for this limitation, I need to increase my release angle and focus on full body extension to create a higher arc, allowing for a steeper entry angle and improved shot consistency. In comparison, Steph achieves a higher release point through full body extension and a controlled follow-through, allowing the ball to travel at a higher arc and increasing the likelihood of a successful shot. As a result, my lower release height is a key limitation as it decreases both control and margin for error. The speed of release is another critical factor in projectile motion. In a 3-throw, athletes do not aim to maximize speed, as high velocity reduces control and accuracy. Instead, the goal is to apply an optimal and consistent amount of force to achieve a controlled trajectory. In my shot, release speed is inconsistent due to insufficient force summation and an over-reliance on my upper body. This leads to differences in force applied to the basketball. According to Newton's second law, any change in force ends up in a change in acceleration, meaning the ball's velocity becomes more inconsistent. This causes variations in shot trajectory and distance, reducing overall shooting accuracy. In contrast, Steph demonstrates a consistent release speed due to efficient force summation through the kinetic chain, allowing for precise control of the ball's velocity and more a repeatable and reliable shooting result. Once the ball leaves the hand, it becomes a projectile influenced by external forces, mainly gravity and air resistance. Gravity acts vertically downward at a constant rate of 9.81 milliseconds squared, causing the ball to follow a curved parabolic flight path, slowing the ball as it rises and accelerates as it descends. Air resistance acts in the opposite direction to the ball's motion, causing a slight reduction in the ball's velocity through its flight. In addition, the interaction between air resistance and backspin applied during release contributes to the Magnus effect. This effect establishes the ball's flight by creating a more consistent trajectory, improving control and the likelihood of the shot being made. In my shot, inconsistent wrist action reduces the amount of backspin applied, limiting the establishing effect on the projectile. In contrast, Steph applies consistent backspin, resulting in a smoother, more stable trajectory and strongly improving shot consistency. Overall, differences in height, speed, and angle of release result in my projectile motion being less efficient, producing a flatter and less stable trajectory. Out of all these factors, my lower release height and inconsistent release speed has the biggest impact as they significantly reduce the margin for error and trajectory control. This makes my shot less consistent and less accurate compared to Steph's highly efficient and controlled technique. Even though this comparison provides useful insights, there are many limitations in the validity and reliability of this analysis. The conditions of my performance were not consistent with those of Steph's, as differences in environment and equipment may have influenced the results. For example, I performed on an outdoor court using a Spalding basketball, whereas Steph shoots in a controlled indoor setting using a Wilson basketball. Additionally, the differences in height may be 5'2" compared to Steph being 6'3", and the skill level means that the comparison is not entirely equivalent.